Welcome to Energy Frontier, the Wyoming Landscape podcast. Hosted by Dr. Holly Krutka, Executive Director of the School of Energy Resources at the University of Wyoming. The show highlights SER's role supporting our mission to promote energy-driven economic development for the state of Wyoming.
Welcome back, listeners. Today, our guest is Dr. Papavassiliou. He is a professor and director of the University of Oklahoma Gallagher College of Engineering, School of Sustainable Chemical, Biological, and Materials Engineering. He focuses on advancing the understanding and modeling of transport processes in industrial and environmental contexts. That certainly has energy applications. He was also my PhD advisor at the University of Oklahoma. So today we're going to talk some science and we're going to talk leadership. So welcome, Dr. Papavassiliou.
Well, thank you for inviting me over, Holly. It's great to be here. I've never been in Laramie. I've never been in Wyoming, so this is a great opportunity for me to visit the state and visit the University of Wyoming.
Well, we're so glad to have you. And we brought in the good weather. It's gorgeous day today when we're recording this. So let's start by having you tell our listeners a little bit about your background and how you came to work at the University of Oklahoma.
Okay, I did my master's and my PhD at the University of Illinois in Urbana-Champaign, and my advisor, your academic
grandfather.
Yeah, that's Tom Hanratty, and he has passed now, but he was a great mentor, and he was a member of the National Academy of Engineering, which is one of the greatest honors that an engineer can have in this country, in the U.S., in addition, he was a member of the Academy of Sciences, which is beyond engineering. So he was a great mentor. I learned a lot from him about integrity, about how to do research, how to be a great mentor and a supportive person for your research group. Anyways, and what I did after that is a little bit unconventional because I did postdoctoral work with a company. So I started working with Mobile Technology Company in Dallas, in Texas. And then I got a permanent position with Mobile Research, and then eventually an opportunity came up at the University of Oklahoma in chemical engineering, and I started as an assistant professor at the University of Oklahoma.
I don't think people realize faculty positions, there's a lot more people looking for them than there are open positions. So it's very competitive.
Yes.
Yeah. Okay. So you came to work in the chemical engineering department. Now it has a much longer name at the University of Oklahoma. Today and you're the head of it, and it's called the School of Sustainable Chemical, Biological, and Materials Engineering. So talk about, first of all, in this context, what does it mean by sustainable?
Yeah, we are, I believe, the only chemical engineering and the first chemical engineering department in the U.S. to have the name sustainable on its title. But what does it mean? Well, you can think of the big, great challenges for humanity in the next several 20, 50 years. What are those? Food, energy, and water. So if you want to put it in three words. So at NSF, when I was working at the National Science Foundation, food, energy, water nexus was the word of the day. And as we become, think about water. So water is dirt cheap today. Mm-hmm. You can get water that you can drink, and it's going to be cheaper than dirt. If you want to order and deliver to you a sack of dirt, it's going to be more expensive than having out of your tap in your home water coming out, clean water that we can drink, we can use in everyday activities. But when water is not there, I mean, think about the California wildfires that were because of dry conditions and the lack of water and rain in the California area just a few months ago. And think about the dryness and the dry weather. I mean, I travel back to Greece. I'm originally from Greece. And you see sand from the Sahara Desert flying over the Mediterranean Sea, going over to Europe, to Italy and to Greece. And this is because of dry weather and the lack of water. And then you have geopolitical and situations like the Arab Spring that has started because of dry patches and the lack of water that led to a lack of food in several countries, and even today we have the situation in Syria. So what we do is we try to work so that we can have clean water. That's a big challenge. When you have water, you also have food. Energy is where we are coming in more as chemical engineers. You look at energy, it looks like we need more and more of it so we can live longer, healthier lives. And so how are we going to make sure that we're going to have food, energy, water in the next several years so that our kids, ourselves as we grow older, can enjoy what we enjoy today? So we need to do all that in a way that we will not run out of water, we will not run out of energy. You look at the AI and machine learning today, the energy needs are growing. And in addition to artificial intelligence that is also needs also additional energy, we need to find ways to produce energy so that we can continue having that. And to me, that's sustainable, so that we can continue having access to energy. We can find ways so that we can have food, we can have water in the next several years. And that's what we mean by sustainable. For chemical engineering, even when I was a student many, many years ago, chemical engineers were always working to have a sustainable environment, even though maybe sometimes the public does not understand or does not have a feeling for that. So optimization technologies, optimization algorithms, chemical engineers, what we're being taught and what we teach our students is that don't waste one single joule of energy, don't waste one single gram of water, don't waste a single watt of energy. Try to design a plant so that it's going to be a chemical plant so that it will actually be the most efficient it can be in terms of energy, in terms of waste. Don't send anything that's wasteful, don't set anything to the environment that's going to damage the environment or the workers of the plant or the communities, the people who live in communities next to the plant. So that's a chemical engineering was sustainable forever. That recently has not been, when I say recently, I mean the last 5-10 years, does not really resonate for the public with high school students. So the general belief is that chemical engineers are probably contributing to the production of microplastics, the production of the conditions that might need to dry weather and so on. So that's the reason that my department decided to add this word up there on the title, so to kind of reinforce this idea that what we do as chemical engineers, we try to work and try through our research, through our teaching, through training our students to contribute to what I mentioned before, that this country, this nation, this humanity is going to have food, energy, and water in the years to come so that we all can enjoy what we can enjoy today for many, many generations.
That's really well said. You know, it's funny. I think sometimes chemical engineers have this reputation that we create some sort of chemical process and then we create a problem. And then our next job is to solve that problem, which probably has to do with waste. But then that process creates a problem, some kind of waste, and we work on that. And so we're sustainable in keeping ourselves employed. But what you're saying is try not to create those problems in the first place. Yes. Think about it as we develop the first initial process. Right. Really cool.
That is correct. Yes.
Yeah. So let's talk a little bit about your specific area of research, which is computational transport processes. So first of all, let's explain what that means.
That has to do with the use of computers, the use of software algorithms, development of new algorithms, new software, so that one can study transport process. So that is in chemical engineering, the transport of energy or heat, the transport of mass, materials, substances, and the transport of fluids, because in the chemical process industry, there are fluids everywhere. In the world that we live, in our environment, the atmosphere is in scientific lingo, it's a boundary layer, air boundary layer, but every river, the ocean, the atmosphere where we live and we operate, it's all fluids. And so that's what that has to do with. Most people do experiments in a laboratory to understand better the physical phenomena behind these processes. But what we do in my research is to use computers to do that and simulate this process in a way that is as accurate as possible.
And the nice thing about computers is it allows you to essentially simulate things that would take a lot longer to test, to try different scenarios you might not be able to test. Do you remember what the conclusion, though, of my dissertation was?
You came up with, you did a lot of simulations that were simulating a process that's called melt blowing in the plastics industry, in the fiber production industry. And what you eventually were able to do is you were able to optimize the dyes that produce these fibers so that one could use one of your correlations and equations to predict how that's going to work with different types of dyes. Mm-hmm. And that is related to energy because in that process, the most expensive and the most energy-hungry part is hitting the air that's going to draw these fibers. And if you can optimize so you can design exactly what you want to produce, you save energy by not hitting the air.
That's true. It was related to energy.
It was related to energy. A lot of it is that.
It's funny, though, because it was kind of early to use these models. They were called computational fluid dynamics to study these flow fields. And really, these melt blowing dyes is what they're called. All they are is you melt plastic, and then you send it through tiny holes, and then the air like stretches it out and lays it down into something called a nonwoven mat. That's how you make waterproofing materials. So, but what we found was that the configuration that was being used is already the best. I don't know if we optimized anything.
Yeah, in some cases, yes. But when somebody wanted to do, we were collaborating with one of my colleagues there, right, Dr. Sambo, and he had the experiments, and his technology is to get measurements at every point and look at his technology. He was using high-speed cameras and infrared cameras to look at the fibers. We're talking about something that was 20 microns in diameter.
Tiny.
Very tiny. A human hair is 100 microns. So it's a fifth of a human hair in width, right? And he was using very advanced optical techniques to be able to look at them. And we could just do all of that with computers. And to set up an experiment would take forever. To set up computing, it took a while. I mean, it was not as easy as it sounds, but then once you get a hold of it, then you can do different cases very quickly that you cannot do in the laboratory. And then the big advantage is that you can discover equations, relationships between all of these things, so you can have a predictive capability for such processes for the future.
Yeah.
Yeah.
I like
so
that.
This is what is important in computational fluid mechanics, to me at least, is to, in the initial stage, to have some type of an experimental guideline, an experimental data point, or an experimental process, so you can compare what the computer gives you to real life. And once you are confident that you do it correctly for one case, then you can move on to do cases that nobody has ever done before.
Right. That's the power of using modeling. Okay, so you have a lot of experience in the fundamentals of interfacial science and nanoparticles in the context of porous media. So that is a lot of jargon. So we're going to break down each one of those terms. So let's start with interfacial science. What do we mean?
Yeah, interfacial science, I think pretty much everybody has some experience with oil and water that doesn't mix, or oil and vinegar. And I think there was a Netflix, or there is a Netflix show lately with oil and vinegar. Anyways, so oil and vinegar do not mix. Where they don't mix because one does not like the other. A molecule of vinegar does not like a molecule of oil. One pushes the other, and then there is an interface. That's where the two phases, the two liquid phases meet. In the same air and water, air, you look at bubbles as they move up. A glass of beer or a glass of champagne, depending on your tastes. That's the bubbles of that gas form because of the what's called interfacial tension. So that's interfacial phenomena. They're important. They're important in our body. They're important wherever, one fluid gets in touch with the other. When we breathe, air comes into our lungs, and the lungs have surface active ingredients so they can get the oxygen through. So, and in the chemical process industry, oil and water and air and fluids are coming in contact several times and in several instances. So interfacial science is how you can move substances across these interfaces, or how you can mix things and understand how the different phases behave at that intersection.
Good. Okay, so what about nanoparticles? That one's kind of simple.
Yeah, it's small particles that are very, very small, that are on the order of nanoscale. So what does that mean? We talked about the fibers that you produce that were 20 microns in diameter, human hair 100 microns. Nanoparticle is, we cannot even see it with the human eye. That means you are 1,000 times smaller in scale than the microns. So that's 100,000 times smaller particles in diameter than human hair. Very, very little tiny particles that we might breathe, we might use in technological applications, but very, very small.
Great. And then porous media, I think a lot of folks listening to this podcast will know that it's because it has so many applications in energy, particularly for subsurface energy, CO2 storage, oil and gas. But porous media is just what? Yeah,
it's a material that has little...
You could say pores. Everyone knows what a pore is.
Right, that are very small, and they're characterized by porosity, how much is empty, how much is solid. That would be a porous material. So rocks, sand, sandstones, even in the process, in the chemicals industry, you might have industrial processes that are full with particles like catalysts, or that they have pores in them. So that these are porous materials.
Great. Got it. Okay, so now that we've defined all those things, talk about the challenges and opportunities with respect to engineering interfaces and the use of nanoparticles for chemical engineering in general, and then we'll go specifically to energy after that.
One thing that I guess I need to say is that nanoparticles, nanotechnology, not with the nanotechnology name, have been used for a long, long time. People might not realize that, but for example, titanium oxide particles, they're nanoparticles, and they are pretty much in every sunscreen cream we use. The same for paint for cars. The titanium particles, they're nanoparticles, they're very, very small, but they're mixed in the paint of cars. So we use them, we see them every day. In biological cases, the recent vaccines that were developed that were DNA-based, eventually you would create nanoparticles that would hold in them one strand of DNA or mRNA, to be more precise. So, nanoparticles are being used in several applications already. Proteins, you can call them nanoparticles. They're nanoscale-sized polymers, globules of polymers. And other places, if you fly with an airplane, I flew in an airplane to get out here, a lot of materials in airplanes are made out of composite materials, polymers mixed with nanoparticles. And these nanoparticles can be used to actually give properties to composite materials that they didn't have originally. So they can be conducting, they can be electrically conducting, or they can be thermally conducting or stronger, and be able to withstand the pressures and stresses that the polymer itself cannot.
So do you know what parts of the airplane? What are you talking about?
That would be, I think now pretty much, if you look at the Boeing, the Dreamliner, the 787, I think is the Dreamliner, most of it is composite materials. So instead of using metal, they use polymers with little nanoparticles dissolved in it.
And it makes it strong and flexible.
Lighter, and saves energy. Because then you can fly an airplane farther with the same amount of fuel. The same for cars. You can make them lighter if you use this type of materials.
Great.
You can use nanoparticles in paint. So paint.
It helps it spread, like paint spread out more evenly along the wall.
Right.
Yeah. Okay. So what about how could any of this be used related to energy, or how is it used?
One area that has potential, and we have done a little bit of work on that in my group, is in enhanced oil recovery. So one of the issues, if you want to recover, after primary production of oil, you might decide to do secondary production or tertiary production. And one way is to do chemical flooding, what is called chemical flooding. So you put some chemicals, mostly surfactants, that push the oil through, and you can produce the residual oil that's left in the reservoir. But if you use surfactants, you lose a lot of them. These are petroleum products. They're made out of petroleum, so they're expensive. And the way that you use them, you put them back in the ground and you push the oil out. But when you do that, you lose a lot of that surfactant. It gets attached to the rock. So you lose it. So at the other side, you get oil, or you might not have enough surfactant to go through. So an idea is to use nanoparticles as transportation vehicles, like buses, that the surfactant molecules are attached to these nanoparticles, and you push the nanoparticles, then the nanoparticles do not attach to the rock, and they can continue, they get to the interface between the brine and the oil, and at that point they release the surfactant, then you can push the
more oil out.
You can get more oil out without losing the surfactant, so in a cheaper way. I don't think this is a practice today, but it can be. It's one area with potential. Composite materials and nanoparticles is another one. And as I said, the moment you do lighter materials, stronger materials that can withstand more stresses, and then you can save energy by just using less lighter pieces of equipment, lighter parts in cars and airplanes.
Isn't that also what has allowed wind turbine blades to get so long?
Yes.
Because they now can be strong and be that long, and that's allowed these much bigger turbines to be built.
That is right.
Can
Absolutely
produce
right. Yes.
more energy.
Yeah.
Cool. Anything else you want to say on that?
No, this I think covers it. It hits a few of the areas that are important for energy.
Cool. So let's talk about, you took a break from being a faculty member at the University of Oklahoma to serve as director of the National Science Foundation Fluid Dynamics program. So first, for those that aren't familiar, let's start with what the National Science Foundation is, and how is it structured?
Yes. The National Science Foundation was established right after the Second World War, I think in the early 50s, I don't remember exactly, with an act of Congress. And what was its goal? Its goal was to support financially and in any other way possible research in the United States on fundamental areas. So the idea is that if any academic or any person in the U.S. has an idea for research, they can submit a proposal to the National Science Foundation, and the National Science Foundation should find a home for it, a division, a program, a directorate that can fund this idea. It was not designed to fund applied research. So if somebody has a patent already on something, or they have published 20, 30 papers, in academia on a subject, the National Science Foundation is not for that. The funding is not enough and that's not the purpose of it. So, and the way it's structured is it is structured in directorates. They're called directorates. There are several of them. One is the Director of Engineering. And the Director of Engineering has a budget of about, I want to say, $800 million per year. And what they do, they use the majority of that. NSF runs very, very lean. There's not a lot of money that goes to salaries. It's very, or travel for the employees there. But its goal is to disperse this money to engineering schools across the country, and its mission is to support educational initiatives and fundamental research to train the new generation of engineers and scientists, so that we can continue being the number one, so that this nation has the number one position leading research across the world, and also to broaden education and research so that not only one or two or three institutions get the funding, but other institutions, like, for example, I'm a professor in Oklahoma, so other institutions like the University of Oklahoma, the university here, the University of Wyoming, all across the country geographically, there is a distribution of funding so that everybody can participate in the research enterprise. And, it makes sense because this is taxpayer money. People in Oklahoma pay taxes, people in Wyoming pay taxes, federal taxes, so they should get some benefit out of that. Yeah, so the work that people do at NSF is, I believe, irreplaceable. It has helped in the last 60, 70 years to ensure that the United States, this country, is the forefront of research across the world. This is the gold standard of research, is what NSF funds. I need to distinguish a little bit. There is also the National Institutes of Health, which fund, the Institutes of Health, they fund research related to illnesses. The National Science Foundation does not do that. They
doesn't do any illness research.
No, it does more fundamental. So if somebody has a bio-related or a health-related application, they would go to ask for funding from NSF if the findings of that work can be applied to any other different to many other different cases, not a specific research. So the budget for NSF, I think last year was close to $8 billion. The budget for NIH was close to $45 billion.
Wow.
So there is a big difference there. So NSF covers pretty much everything. NIH covers research that has to do clinical trials, that type of stuff.
And that stuff is expensive.
It's very expensive. Right?
And National Science Foundation, or NSF, those grants are really competitive, right?
They're extremely competitive. The rate of funding might be, I don't know, I'm not so sure, maybe between 10-15%. So one in 10, one in 8 proposals gets funding. And the way they do it is they actually have a group of peers, a group of other people who are experts in the subject area of a proposal, and they're looking at a bunch of proposals. Let's say you have a panel of maybe 15 experts, and you have about 40 proposals, and they hash it out. They talk about them, the merits, the impact of each one of them, and then they decide out of the 40 proposals to fund maybe 4.
Yeah.
So it's very, very competitive.
So talk about your experience and what did you learn during your time at the National Science Foundation?
To me, it was a wonderful experience. That, as you mentioned, I was the program director for fluid dynamics. So if you are in that position, you can help shape the research in that area in fluid dynamics for the whole country in the next several years. Of course, I was there for 3 years. NSF works like this. Half of the program directors they're called rotators. They go on loan from universities or national labs and so on, and they stay for maybe anywhere between 2 and 4 years. They cannot stay longer. And so what was great was the interaction with young scientists. So, my colleagues who were just starting out, and they would come and meet me and share with me their brightest, the best ideas. And I could not guarantee anybody's funding, and it's a competitive process, but it was a great opportunity to see what they do and share in their excitement for research. In addition to that, there were these cross-cutting initiatives and relationships between the National Science Foundation and other places and other funding agencies. One of the highlights for me was that I helped. My program was fluid dynamics, and then there was a particulates and multi-phase program in the same division. And the two of us, we worked with CASES. CASES is the Center for the Advancement of Science in the International Space Station. Okay, what does that mean? Well, I did not know that until that point. The International Space Station actually is a national lab, like Livermore or like Los Alamos.
I didn't know that.
Exactly. And so what we did is we worked with CASES. CASES could figure out how to teach astronauts to do experiments, how to fly, how to send experimental equipment up to the International Space Station. And they work with us at NSF to put together solicitations to do experiments in the International Space Station that would help with life here on Earth. So the goal was to test cases that gravity cannot allow you to understand what's happening if you do the experiment in Earth, but you can do that without gravity. So interfacial phenomena, things like that have to do with charges, electrical charges, and that type of thing are dominant effects, and gravity does not allow you to do that here. So we managed to fly eventually, I think, 2 or 3 of the 6 proposals that were funding. They flew up there, and now they're still doing that. Other programs now have contributed, are doing it. The bio, the catalysis, fire and flames, because fires and flames in a space vessel are catastrophic.
Not good.
Not good. Yeah. So that was very, very interesting to me, and to see how you can work with others within NSF and outside of NSF to make sure that we do the best research possible.
It's so important in all research. That's one of our big focuses here at the School of Energy Resources, and the word we use is just multidisciplinary research, but we're bringing in all of these different folks to tackle kind of common topics, and they always have really different perspectives. So it's the way to actually make your research impactful long term. Okay, so then you did your 3 years at NSF, is that right? And then you came back to the University of Oklahoma and went back to your role and doing your research. So what would you tell someone who wanted to learn more about the field of computational transport processes, or students interested in pursuing that field? Where should they look or to learn more?
Yeah, this is, to me at least, it's an exciting field. I think there is a lot of future with computations. even more so with the capabilities of the computers. To give you an example, when I was a graduate student, I was using one of the biggest, strongest, fastest computers at the University of Illinois, and the power that had, I could have that on my cell phone,
now.
Now it's multiples of I could have it in a cell phone like 10 years after
Really?
It's amazing. My laptop can do more than I could do back then in the supercomputer.
Have you opened that dissertation that we did?
Yours?
Yeah. It looks so elementary. Like the resolution on the images is so low compared to what you would see today.
So add to that, the new capabilities the last few years with AI, machine learning, and network analysis. I have heard, this network and node analysis. So one described it to me. It is as if up until now we're looking at things with our human eye, trying to see what we can see with our eyes. And all of a sudden, when you're using this type of technology, it is as if now you have a microscope, so you can see much, much more in detail. Now, if you want to be involved, now every middle school, high school kid has a phone, right? They're very familiar on how to use very, very advanced and capable computers. A smartphone is a computer and connects to other computers. But what I would advise is try to get involved a little bit so that you know how to do things at a deeper level. So what does that mean? Maybe try to be in a computer programming class, learn something like Python, or it doesn't matter which one, just to get a feeling how these computer languages work. For example, Python is very common now. And maybe take a look to understand a little bit how computers work, what's a CPU, GPU, what might quantum computing, what that means. So it doesn't need to be in a lot of detail. When I started my work, I knew a little bit of programming. I don't remember how much of programming.
I didn't know any till I started. We just did a little bit, but you had to program even just to use the supercomputers.
Right, how to run. So learn a little bit of that, and then I think it's a wide open field, and there are the interesting thing to me, one other interesting thing, an additional interesting thing, is that when you do computations for research purposes, you can go from the subatomic level. You can do computations using technologies and algorithms that I can actually talk about electron movement, quantum level. You can do atoms, you can do molecules, you can do bigger molecules in what's called coarse graining, or you can do mesoscopic, macroscopic, all the way to process, to a whole chemical plant or a model that can predict the weather in the state of Wyoming and the wind patterns for the next week.
We need that.
So you go from
our predictions are lacking.
Yeah, the same in Oklahoma when Oklahoma is
Oklahoma. You guys could see it coming for 1,000 miles.
That's true.
No, they could tell you that. It was incredible in Oklahoma. They can tell you what time it's going to start raining at what intersection. And here they're like, there's 1% chance of snow. I'm like, it's snowing now.
Yeah.
So, okay. I think what I'm hearing you say is really there's opportunities. There's always going to be opportunities in the computational area, but it might be worth just instead of just using AI or just using computer models, try to lift the veil a little bit and try to understand what's going on there.
A little deeper.
Yeah.
Right.
And it gives you an advantage. Okay. So on this podcast, so we've talked about a lot of different things, but we always want to talk about leadership. And you being a department head, I wanted to ask about this because I think that's one of the most challenging leadership roles there is, especially in academia, at least. And the reason is because you're a faculty member, you go through the tenure and promotion process. Then when you become a department head, that's not really a promotion, at least that's permanent, right? But you have to lead a team of your peers who you will go back to being a peer, not a department head. So can you talk about how do you do that? What are the strategies that you use?
Yeah, I cannot speak for everybody, and actually maybe this is a good thing that people do this job and then they go back to being a faculty member. So for everyone who does it, every personality has some positive things. There are some pluses with them, the way they do things, and some minuses. So since you might rotate out fairly after maybe either 4 years or 8 years or something like that, if you are to do damage, you don't do damage for a long time. And then somebody else comes who has strong traits that where you might have weaknesses, and that can help the process. Now, there are many challenges. I mean, there are two things. One is the department chair, the department head needs to have good relationships with the rest of the college, the rest of the university, so that they can go there and get support and be in tune with the priorities of the upper administration outside of the unit, and be able to get resources from outside of the unit. And then the second part is to be able to manage people, which is always difficult, especially in academia. People might have strong egos. They're more independent.
Yeah.
That's why they're in academia. If they were less independent, they would have been someplace else. So, so you have these very strong independent personalities. And I don't know if it is a strategy, but I'm a good listener. I listen to what they have to say. I'm very patient, both with the faculty and with the administration. So if we want to do something, I might go second, third time to the administration to be able to do it. And you have to be fair. It often feels that there is a pie, and this is how big the pie is, and everybody wants a bigger and bigger chunk. I'm talking about resources. I'm talking about lab space, for example, or computational facility space, or number of undergraduate and graduate students that you can have in the group. So you need to be fair as you distribute all of that.
How do you know if you're being fair?
Well, it needs to be transparent. It needs to be in a way that everybody understands what is the goal of the unit. So everybody needs to share in that. So you need to have an objective. And everybody needs to be on board achieving that goal. And then it becomes obvious what it needs to be done, and what activity is an activity that contributes towards getting to that goal, achieving that goal that you set for yourself.
It's well said. I think you said something really important at the beginning about maybe it's good that you end up going back, but I think that's an interesting point that maybe you could think about from leadership as like, you should probably, even if you're not hopefully going back, you could still think about your leadership role as if you were.
Yes.
Right? Like, if is this decision,
that's absolutely true.
Or the way, you're going to have to make hard decisions sometimes, and someone's not going to be happy. But if you're transparent and you're fair and you communicate it, then, that's the best you can do.
Yeah, that's absolutely true. This is true for a role as a department head. Actually, it was true at NSF, because you are judging, you're helping to fund research from essentially your peers. You're going to go back and be that, and treat them the way that you wanted to be treated when you were on that other side of the room. So, like a golden rule.
That is, that's super insightful. Very helpful. Okay, so for usually our last question, we ask our guests, what's your favorite place to visit in Wyoming? But I'm not going to ask you that because you just got to Laramie last night.
Laramie.
You would have to say Laramie since it's the only place you've been. So instead, I'll ask something different. So what's one thing you'd like our listeners to know about you?
Okay.
Here, I got a better one. What was I like as a grad student?
I can answer both. You were great as a graduate student. You were one of these people who do things, not spend a lot of time, not doing and procrastinating. You were very, very effective, and you were extremely smart and hardworking.
But too headstrong. Do you remember when I tried to tell you that we were running the modeling long enough, and you were like, obviously we're not, and I wouldn't listen.
Yeah, that's the goal. A successful graduate student is one who starts, there is mentorship and all of that, and then eventually you get to the point, that's the goal, to get a person who would be their own researcher, to be an independent, sometimes headstrong, but knowledgeable, and being able to justify why they do what they do, and learn how to write, learn how to do research, and eventually go out there and continue this and pay it forward to somebody else.
Yeah.
let me say something about things to know about me. One thing, and I don't know how many people know that, but it has to do with Game of Thrones. Okay, so I started watching that late. Actually, after most of it was already there, and I liked it, like pretty much many.
Like everybody.
Like everybody. And then I started reading the books after I saw the movie. And what I saw there is that the George Martin, the author, was extremely creative. I was reading the books, and it was as if I was reading medieval history, right? So I admire a lot these people who can create in their mind the universe that's so complex and so intricate and nuanced, and they can bring that to life, either through the pages of a book or through a movie. And I just could not stop reading them. I read one after the other. Of course, I would forget what happened in the previous one, but it was very obvious that he did not forget what was happening in the previous books. And that was something amazing to me. I just admire this type of creativity. And also somebody can be that creative in science and engineering, kind of develop something that nobody has seen up until that point, and develop it in their mind, and then eventually try to see how you can make that, either turn it into an experiment, a hypothesis that you can justify, and into something that can be useful and insightful.
Yeah.
So, yeah.
Don't be limited by what's been done.
But, going back to you as a graduate student, if you have anybody who's like you and you want to send them all the way to Oklahoma, feel free anytime.
We'll let you know.
We'll be very happy to have somebody like you clone you and have other students.
No. I actually, I wouldn't have gotten a PhD if it wasn't for you. I wouldn't have even thought about it. I think a lot of Americans, especially when you're in chemical engineering, you can get a job from undergrad really high paying. Yeah. So thank you for, I don't know, just convincing me to do undergrad research, because now I wouldn't have this job if it wasn't for you.
Yeah, well, thank you. I mean, it's exactly like this. You need to have a person who has intellectual curiosity and wants to maybe sacrifice a little bit, because even today, if you get a job, some of our graduates who graduated back in May, right? They get a job, they might make around $100K a year working in the energy business. If you want to do a PhD, you have to study and study and study for another 4 or 5 years and make, 35K a year. So you need to be a person who wants to do it.
Yeah.
Not for the money.
But I also thought OU was going to win another national championship, and I wanted to be there for that, but they still haven't won one.
But they won 3 in a row in softball, right?
Yes, that's true. I should have been.
Gymnastics, they do win some national championships in gymnastics.
Yeah.
Yeah, football is going to take a while the way we...
Well, we're not going to go there, because that could be a whole nother podcast.
That's right.
This is the Energy Leadership podcast, not the football podcast. So, well, thank you so much for all you do. Thank you for all you've done for me, and thanks for doing the podcast.
Absolutely. Thank you for having me, and thanks for saying all these nice things about me.
Thank you for listening to this episode of Energy Frontier, the Wyoming Landscape, the podcast that highlights the School of Energy Resources at the University of Wyoming. You can expect a new episode of Energy Frontier every Wednesday on Apple Podcasts, Spotify, or wherever you listen to podcasts. See you next time.